Hello everyone, welcome back to Math with Allison. Today we're working in our sequences and series, and we're going to be talking about the convergence of a Taylor series. So let's go ahead and dive into it. First, we have a little reminder on what a Taylor series is. So here we have a Taylor series centered at x equals a. That's going to be equal to, and first we have it written out just term by term, so if you want to read through that, take a pause. Otherwise, I'm just going to talk about the summation notation. So we have the summation n equals 0 to infinity of the nth derivative evaluated at x equals a divided by n factorial times x minus a to the power of n. And a little side reminder, right, of Maclaurin series is where it's centered at x equals 0. So let's talk about its convergence. So what does it mean for a Taylor series to converge? So the series converges to the actual function if the remainder term, so right here we're calling the remainder term Rn of x, that is going to be a term super far off in the polynomial series, right? So we're just getting really deep into the series. We have f of n plus 1 evaluated at some c, where c is between x and a, divided by n plus 1 factorial, and then times x minus a to the n plus 1. So we're just picking a term really far off. Now, we know it converges if these super far off terms, if their limit as n approaches infinity, converges to 0. So it's basically saying at some point we're adding such a tiny number to our series that it's not making a difference anymore. So it's like it's converging to that upper bound, right? We're never going to cross the upper bound. We're just going to be adding numbers so tiny that we get super close to it, but we don't cross over. So that means we want those ending terms to go to 0. So the notation might be a little confusing, so let's just talk through an actual example. We want to show that the Maclaurin series for e to the x actually converges to e to the x for all values of x, not just specific values. So the first thing we have is a reminder of what the Maclaurin series is. We have the summation n equals 0 to infinity of x to the power of n divided by n factorial. So what we want to show is that these are actually equal to one another. And we're going to be doing that by showing the remainder, some really far off term, does for sure go to 0. So here, let's go ahead and find what this is equal to. So this is equal to the n plus 1 derivative evaluated at some number c divided by n plus 1 factorial times x to the power, times x minus a to the power of n. Remember, in this case, it's a Maclaurin series, so we know this a is equal to 0. Okay, so what is always the derivative of e to the x? E to the x. So this is going to be e to the power of c divided by n plus 1 factorial times x to the power of n. So right now, what do we know about c? We know c is somewhere between 0 and x. So what does that mean about e to the c? E to the c is somewhere between e to the 0 and e to the x. So in other words, it's bounded between 1 and e to the x. So that means our remainder term is less than or equal to e to the x divided by n plus 1 factorial x to the n, right? Because e to the c is less than or equal to that. So I'm going to erase this right here so we can write out our limit. We have the limit as n goes to infinity of our remainder term, Rn, is going to be less than or equal to the limit as n goes to infinity of e to the x over n plus 1 factorial times x to the n. Now, what are we taking the limit of? The n values. So notice here our e to the x doesn't have any n values, so we can just go ahead and pull it out. So we get x to the n divided by n plus 1 factorial. What do we know about this limit? We know the limit is going to go to 0. Factorials, the denominator, is going to grow a lot faster than the numerator. So the denominator is going to be getting big so quickly that the numerator can't keep up. So it's going to go to 0. So this is equal to e to the x times 0, which is equal to 0. So since at some point the terms get so tiny, they don't add much anymore, we know that this is going to converge. So I'm going to say the summation n equals 0 to infinity of our actual terms, x to the n divided by n to the factorial, converges to e to the x. So we know this actually equals our function. If you guys want an actual proof for why this limit goes to 0, let's go ahead and think about it. One way to show it is if the limit as n goes to infinity of a to the n plus 1 divided by a to the n equals 0, then we know it converges to 0. So if we were to think about this like a sequence, right, we would have the n plus 1 term, so x to n plus 1 over n plus 1 factorial times, that's going to be n factorial over x to the n, right? I just multiply by the reciprocal. So what does this simplify to? First, we have the x to the n's cancel, leaving us with just an x in the numerator. And then the n factorial cancels, right? Because this is n plus 1 times n factorial. So we're left with n plus 1 in the denominator. So what is this with the limits, really? This is the limit as n goes to infinity of, we can pull out the x, right? Because the x doesn't have any n terms. So this is x times 1 over n plus 1. This is equal to x times 0, which is indeed equal to 0. So that's another way to show that that for sure goes to 0. Let's try one more example. We want to show the Maclaurin series for cosine of x actually converges to cosine of x. So let's go ahead and do the same thing. We know that cosine of x is equal to summation n equals 0 to infinity of, that's negative 1 to the n, x to the 2n divided by 2n factorial. Let's actually show that these are equal. And we're going to write out the remainder term. So this is equal to f, the nth plus 1 derivative, evaluated at some number c, divided by, that's going to be n plus 1 factorial, and then x minus a, but our a is equal to 0, so I'm just going to say we multiply by x to the n. Okay, so question is, what's the n plus 1 derivative? Let's go ahead and think about all the derivatives of cosine. So if our function f of x is equal to cosine, let's list out our derivatives. First derivative, negative sine of x. Second derivative, f double prime is equal to negative cosine of x. Third derivative, positive sine of x. Okay, and then in our fourth derivative, we actually go back to the function cosine of x. So what are all of these bounded above by? If we think about the graph, right, this is cosine of x. We start at 1 and then we go down like this. If we start at sine, then we go something like this. Not a perfect drawing, close enough. What are they all bounded above by? They're all bounded above by y is equal to 1. So every single one of these numbers is going to be less than or equal to 1, no matter what derivative we're at. So we know our remainder term is always going to be less than or equal to 1 over n plus 1 factorial times x to the n. So we can just rewrite that, right? Beautiful. Our remainder is always going to be smaller than that. And that is very helpful in our limit. So the limit as n goes to infinity of our remainder term is going to be less than or equal to what we just showed, right? So this is going to be x to the n over n plus 1 factorial. And we just showed that this does equal 0. So this is for sure going to converge to 0. Since we know this goes to 0, then we know this equality is actually going to hold. That cosine of x is well approximated by this power series. So that's all I have for us in this video today. If you enjoyed it, I have many more like it, so make sure to check out my playlists. They're linked down below. Otherwise, please give this video a thumbs up and comment other problems or topics you'd like to see done. Thanks for watching.